So our topic at hand today is, I think, a fairly popular topic. Because vehicles misfire all the time, and sometimes they can be a little tricky. You don't want to just parts cannon it because it could be a multitude of different things causing a misfire on a vehicle. So you don't want to just want to go straight to the parts cannon. But we have a couple different ways or a couple different things that we can do to test for a misfire to see whether or not which one of these four things isn't working. Because remember, for combustion to occur in an engine, we need to have air, we need to have fuel, we need to have spark, and we need to have compression or some sort of an ignition source, we'll say, instead of spark, ignition source. So we need to have all four of those things in the proper amount. If we're missing one, one's too high, one's too low, it'll cause a misfire in that cylinder. So it could cause multiple misfires depending on where the problem might be. So let's just address these in order. A couple different tests, couple different things we can look at in order to figure out, where is my problem and narrow it down without having to necessarily disassemble the engine to get to it, right? So first one, dealing with air and fuel, it's going to be our oxygen sensors. So oxygen sensor is going to measure the amount of oxygen left over in the exhausts. So this is going to help dictate how the vehicle runs. So typically, the most common one, even since back in the 80s, even with a single wire sensor on a GM, right? Remember those? And now we have the 4-wire heated oxygen sensors as well. But what they do is they will read the amount of oxygen remaining in the combustion's exhaust. So it signals the computer whether or not it's rich or it's lean. Now, a zirconia sensor produces a voltage, so it's not provided with a voltage, so it actually produces a voltage depending on the amount of oxygen in the exhaust. Roughly 0 millivolts to about 900 millivolts, usually not quite zero, maybe like a tenth or a hundredth. Most accurate 455 millivolts, which represents a 14.7 to 1 stoichiometric air-fuel ratio. And due to the way it reads, the ECM has to switch backwards and forwards from adding to subtracting fuel. So it is a zirconia membrane in here. And sometimes there's a heater, sometimes there isn't. But there's these electrodes here that will measure the reference air. So you do also need outside air coming in on the backside of it. And if we look at the sensor, usually there's like a crimp back here, but it's not crimped all the way. Here's probably a better example right there. The air is able to get through into there. And that will provide the reference air to the inside of this, which will allow it to reference it versus ambient air. How much oxygen is in that exhaust gas? Is it more or less? And it generates a voltage based on that difference between the two. So like we said, ideal air-fuel ratio is 14.7 to 1, falls right here in between 0.4 and 0.5, so it's about 0.4 and a half, so 455 millivolts. It is between a narrow band of voltage for its accuracy. So you may also hear this as a narrow band oxygen sensor. Could be what you've heard it called. And as I said, it switches back and forth, so it goes rich, lean, rich, lean, rich, lean, rich, lean, rich, lean. So you're going to see the voltage cycle back and forth. So we're down to about 0.1 up to about 8.5. So that is just a typical voltage output for a zirconia oxygen sensor. And that's what you would read if you're testing with a scope. Now, we also have AF sensors, or air-fuel ratio sensors, which are increasingly common nowadays. They look very similar, and they work fairly similar, but they're a little bit different. They actually read opposite of what you would normally see on a zirconia. So it does have a reference there. It does have a zirconia membrane. It has two zirconia membranes, actually, and they're kind of sandwiched together in between this monitoring chamber right here. Now, the goal of the oxygen sensor, or this AF sensor, is to keep this monitoring chamber at stoichiometric, or lambda. That's a lambda signal symbol right there. Lambda of 1. So that would be stoichiometric 14.7. So it has this pumping cell that provides the current, and depending on which way the current flows, it'll move oxygen in and out of this monitoring chamber. And then there's a zirconia membrane. We'll say, all right, so how close is this to stoichiometric at that point? It wants to keep it around even. So it's basically two zirconia cells mated together in a planar form, which is what they call, it's like plywood, right? Different plies. The AFR sensor uses an entirely different operating strategy, though. One zirconia cell is used to measure oxygen content in the exhaust stream itself. The other zirconia cell is supplied with a very small electric current from the PCM capable of moving oxygen ions positive or negative in or out. Electric current achieves a stoichiometric ratio between both cells. It's known as a pumping cell. It also operates at roughly double what the zirconia sensor is. So it's about 1200 degrees. Zirconia sensor is around 650 degrees or so, 640 degrees Fahrenheit. So like I said, it would pump it in between here, tries to keep it at lambda of 1. It's going to read the voltage in there, and the pump current will change slightly, but it's such a small amount of current that you really can't measure it without taking the circuit apart, and even then, it'd be a little tough. So as PCM monitors the varying current, it will convert that current into a voltage value PID, so you actually can't test the sensor directly. Best way to test an air-fuel ratio sensor signals by monitoring the actual PID itself. It's possible to monitor the sensor varying current, but the changes are very small and difficult to monitor. You need like a microamp clamp, which are hard to come by, and they are pretty pricey for what they are. So, like I said, it converts it to a voltage, so you'll just see you'll see a normalized voltage in the data, right? So in this case, lambda voltage 3.3, which equals 14.701, which is 0.66 normalized voltage there. A positive flow lowers the resistance and increases the amperage, thus increasing the voltage. So we can just see rich is going to give you negative current flow, lean is positive current flow, and we can see the differences in there. So it is the opposite of how our zirconia sensor works, by the way. So we mentioned this a little earlier. When the fuel mixture becomes richer, the voltage should decrease on the air-fuel ratio sensor, whereas the zirconia sensor is going to be higher voltage. Under lean conditions, it's going to be the opposite. So AF voltage goes high on lean, zirconia sensor goes low on lean. So they work opposite of each other. And we'll be able to see that a little bit later when I give an example. Which leads us into fuel trims. So our oxygen sensors feed into our fuel trims, and fuel trims can definitely help us when it comes to time to diagnose, is it a rich miss or is it a lean miss, and what possibly could be causing it. So with fuel trims, the often understood fuel trims, as we said earlier, you want to keep that engine running at 14.701. So the front oxygen sensor, perhaps it's reading lean. So if it's reading lean, that means, oh, we need to add fuel to bring it back to stoichiometric. So it's going to have a positive fuel trim to correct that. And then it's going to overcompensate. And then it'll say, oh, now we're rich. So we got to pull some fuel away. So then we come down here, negative fuel trims, brings us down a lean condition, and so on and so forth. So like we saw earlier where it cycles back and forth, rich, lean, rich, lean, rich, lean, that's what we would see on a front sensor. Rear sensor, theoretically, should be fairly flat because if the vehicle's running properly, it should have the same amount of oxygen no matter what after the CAT. But the fuel trim's a window that allows you to see what the computer's doing to control fuel delivery and determine how the PCM's adaptive strategy is working. So like I said, there is a relationship. The oxygen sensor is going to build in the short-term fuel trim. That's going to react to what the sensor's doing. Over time, if there is excessively high or excessively low short-term fuel trim, it is going to feed into the long-term fuel trim, and that is going to adjust the long-term fuel trim. So over time, we can see how they affect each other. Short-term fuel trim reacts quickly. Long-term fuel trim takes a while, and it trails what you would see in the short-term fuel trim. So we're going to look at some scanner data and see what we can see with those oxygen sensors there. So we're going to create a vacuum leak in the car. Took the brake booster hose and kind of cracked it open. Observe the oxygen sensors in relationship and comparison to fuel trim, and then we'll repair the vacuum leak and see what happens after that. So here's an example on a Subaru. The rear oxygen sensor is going to be showing, should be high on one side because there shouldn't be, if the CAT's working the way it should, there should be like no oxygen left. Air fuel ratio sensor in here is going to be, should be around about 1. We want to keep that around 1. Now, Subaru is a little bit different than most manufacturers where they label their short-term and long-term fuel trim differently. So this is air fuel correction. which is going to be your short-term fuel trim, which is correcting in the moment. And then air fuel learning is going to be your long-term fuel trim. So what it learns based on the correction, how it should be. So that I guess they make sense, but it's literally different than what all the other manufacturers do, right? It's not OBD2 standard or whatever, but this is being the OEM side of the computer anyways. So normal idle, around about 1, and then rear oxygen sensor is reading up at 0.8. And then we go to crack it open, and then we'll see it slowly creeps up here. This is a little bit of a crack in there, just showing a small amount. And then we get a positive 2% correction. We move over a little more. We crack it open a little more. Now we get a 6%. And then we get our air-fuel ratio sensor kind of creeping up a little bit there. Long-term fuel trim is now correcting as well. It's up to 4%. Then I crack it all the way open. It gets up to 35% short-term. And then it gets up to 7% over here. So that's 6% in the long-term fuel trim. And it took a little while to react and get back up to the 7. As a matter of fact, the problem had corrected itself by the time it even got to 7. So I closed the hose back up, and then immediately it went rich. Now, why did it go rich? Because we were adding a ton of fuel. We were adding 35% more fuel to the engine when it was running that lean. And that's pretty much the extent of the correction on this car. So then it went down to 0.84 down here. It's at 0.84. And then the rear oxygen sensor went way up to full rich because it was just pumping so much fuel. And then eventually it adjusted. But the short-term fuel trim got all the way down to negative 4%, while the long-term fuel trim was still at 7% at its max. So as you can see how it kind of trails the short-term fuel trim. And then eventually it kind of corrected its way back down. And then over time it would have corrected all the way back. We can see how it reacts, how quickly it reacts to putting everything back together. And then to compensate, we get a negative fuel trim there. So there is a rule of thumb with these. This is generalized for long-term fuel trim, but you also could use use it for short-term fuel trim in the short term. So plus or minus 5%, that's normal. That's going to be doing what it's supposed to do, managing it within normally expected parameters, right? It's roughly plus or minus 5%. You get the plus or minus 6% up to plus or minus 19%. It's compensating for a possible wear and tear maintenance issue. So clean, inspect, and service whatever the maintenance issue is. General rule of thumb from when I went to tech school was if you see 10%, you probably have a problem. 10% either way. More than likely, you're going to have a problem. And then anything over 20% correction in either direction is probably going to be the one to set off your engine light. Because that now means it's going to have an excess rise in emission standards. So it's going to set a code. It's going to turn on your engine light at that point. I've seen pretty often, even in that range, you'll get an engine light too. But I mean, that's just mandatory over 20%. You're going to get an engine light. And that's probably going to be a 171, 174, system too lean, system too rich, and that sort of thing. So there's just another table to kind of give you the lowdown on that. So roughly 450 millivolts is going to be 14.7 to 1 on a zirconia sensor, which means I don't have any correction needed because I am stoichiometric. If it's going to be rich, it's going to be low, and that means it's lean. So I send a rich command. So low is lean, send a rich command. It's going to add fuel. High is rich. It's going to send out a lean command, and it's going to decrease the pulse width by subtracting fuel. So if I were to go into the freeze frame data on a code, I could see it in there. If I go into the live data, the current data stream on the vehicle, I probably will see it there too, as long as it's still not running properly, right? So that's just one way we can tell our air and our fuel, air-fuel ratio, all of those sorts of things just from reading the scanner data. Also with fuel, we can talk about testing the fuel injector itself, because a failed fuel injector could be causing this issue, right? So we can check an injector 3 different ways. We can check it electrically, mechanically, and hydraulically. So electrically is going to help us verify the circuit integrity. It's going to verify the component is actually operating, or at least the driver is operating. And we can see how it's operating. Mechanically, we can look at the current flow flowing through the injector and verify that it actually did open, mechanical motion. And then hydraulically, we can see the pressure change or drop every time it does open, and then verify the state of flow with it. So verify that it is actually flowing in there. So we'll see. And it's going to look something like this. So we got the yellow line, channel 1 is electrically. The green line is current flow mechanically. And then there is my, fuel pressure. There, the blue line. So we can see everything on this injector. And this is a known good injector. It's usually a good idea to test on known good things, just so you know what good's supposed to look like. So for example, voltage. Here's just a standard top feed injector. It's going to have constant power from the battery, and it's going to be grounded by the injector driver. And of course, the fuel comes in through the top. It's got this little pintle down the bottom. It's going to seal the fuel off from spraying. And then it's got an electromagnetic pintle in here. So when I supply voltage to it, I pull it down to ground, that is going to turn on that coil, becomes an electromagnet, pulls that pintle off the seat, starts spraying fuel. It's going to spray it for a set amount of time. Once that amount of time is done, what did I say we have in here? We have a coil. So anytime a coil is holding voltage, it's going to store it. All right, so we're going to see once it releases, all that stored voltage has to go somewhere, so we're going to get that kick at the end. So we're going to see a spike. And then this little bump right here is the actual point where that pintle closes and stops spraying fuel. So I can see how it's grounding it. I want to make sure that's nice and fairly squared off. If it's curved, then I have an indication of an issue with the ground side. It's not pulling it down to ground fast enough. Or the driver, I guess. Current flow, same deal. It's going to be going to put it on the power side of the injector and see how it goes. And we're going to watch the current flow. And it should be a nice smooth ramp, kind of like this. Now, what I see here, that is the point where that pintle actually leaves the seat and starts spraying fuel. So if I don't get this bump right here, it may not have opened on that cycle. Also, if you watch this, if it opens here, there, everywhere, it's kind of moving up and down in there, mechanically, internally, it probably has an issue, probably a bad spring, because it's not opening at the same rate every time. You want to see it. If you're looking at the same injector, it should be roughly in the same spot, as long as you're at the same basic RPM. It might move a little bit, but if it's going wild up and down and all that, then you have a problem internally in the injector. And then, of course, when it closes, no more current flowing, so it just goes down to 0. And then with fuel pressure, in this particular case, it didn't show a terribly large drop. Showed a drop of just a couple PSI. It gets from like 35 down to like maybe 32. But what I did like to see was when it closed, well, it's flowing, and then all of a sudden the door closes. You still have that fuel going in there, so you get a little spike in that fuel pressure, and then it eventually levels back off to 35 over here. But you did see a spike in fuel pressure when it closed. It pushed more fuel back in the line, so you got an excess spike in the injector. So I can check an injector in all 3 different states. Pretty cool. Now moving to ignition testing. So coils, most vehicles is coil on plug nowadays, but you can see what's going on in the combustion chamber with the spark plug as well. An ignition coil works on the principle of mutual induction. So that's the transfer of energy from one coil to another when they're placed in close proximity to each other. So you see we have a common iron core. It's usually an iron core. In this case, we have 10 turns of copper wire on the primary side and 1,000 turns on the secondary side. The coil connected to a voltage source is primary. Second coil connected to the output is the secondary winding. So in this case, we have 100 to 1 difference. 10 times 100 gives us 1,000. I have 14 volts and 14 amps going in, which gives me 196 watts to play with. When that magnetic field lights up and then it collapses, it's going to send that 196 watts across. But since we have a 100 to 1 difference, voltage goes up by a factor of 100. So 14 times 100 gives us 1,400. And the current goes down by a factor of 100. So I get 14 down to 14 hundredths of an amp. So that's why it's going to hurt, but it probably won't kill you, because the voltage is what hurts. The current's what kills you. So if you've ever been shocked by the business end of a coil, you'll know it. Probably don't need coffee that day, but more than likely you're still here. Right. And it's going to look kind of like this. We found this little animation on YouTube one time, and it illustrates it pretty well. It's a simplified coil. Turn it on, starts dwell, which means it's going to start charging the primary coil. Once it generates a magnetic field, we remove the power. It's going to collapse, goes over to the secondary coil, and that gives us enough voltage to cross that gap and make a spark. So that's, in a nutshell, how that works. And it probably looks something like this. This is out of a textbook, but it's your textbook looking ignition event. So dwell starts here. We have these little coil oscillations that should start off. Once dwell starts, that's the energy getting into the coil. Then it'll level off for a bit, and then we get the firing line. That is the high voltage required to cross that gap to start the gap. Requires way more voltage to start the gap than it takes to finish it. So we'll have a nice high firing line. And then we have a spark line over here, which is going to be considerably lower on the line. That is the spark actually occurring. We should see some turbulence in there. We can tell by whether it's going up or down as to whether it's rich or lean. Then depending on how efficient your coil is, nowadays they're a lot more efficient than just the one coil that powered your cap and rotor style with the spark plug wires. It's going to be way more efficient nowadays. So you don't usually see as many oscillations. But that's just the excess voltage ringing out from the coil. And then it goes back over to dwell again. And then we start dwell. So that is just one cycle on an ignition coil. So how can we test this? I'm going to talk coil on plug because that's the more common system nowadays. You can do some variants of this on a spark plug wire equipped system. Easiest one is ignition coil signal. You don't need anything special, just a back probe, and you're going to check the ignition control circuit. And usually it's just going to be a 5-volt signal. It's going to send out a 5-volt square wave. So in this case, from here to here, it just goes from 0 to 5 volts. That is dwell. It's signaling the coil to go into dwell and start charging the primary side. So it just switches it on, and then you see how that lines up with the dwell part, and then we get the firing line right there. Primary voltage. It's going to be checking the voltage side. I can just connect to the ignition coil primary circuit once again with a back probe. Easy enough. In this case, on this car, it doesn't give us that great a detail just because of how the coil is wired. Some modern coils, if they have the igniter kind of built in with the ignition control module and built into a coil, a lot of Asian cars are like that. If they're built in like that, sometimes you're not going to get the greatest primary side. I do see where dwell starts. I do see where it fires. I don't really see much in the spark line, and then it just kind of goes back to not a lot of detail on that side of things. So if we were to compare it with the secondary, you can see it right there. Dwell lines up, firing lines up. So at least you can see whether or not it's firing, but not as nearly as much detail as the secondary. And then for secondary voltage, we're going to connect the spark plug or coil wire or directly on the coil on plug systems. In this case, I use one of our universal flags. Set it on the coil and see what you can get. Sometimes you got to move it around a little bit to get a good picture just because of, like I said, might have an igniter built in. It's going to look something like this. There's dwell, and then it comes up. There's my firing line, and then there's my spark line. The negative voltage there, that's probably just caused by the probe placement. It's the cleanest signal I could get. Generally, it's just going to be going up, not down. Just the sensitivity of the probe, I guess. And then we can kind of see this curves down, which is actually not. Once again, that's related to probe placement. And then primary current, connected to the ignition coil feed circuit, and then it's going to look an awful like an injector current minus the dip right there. So it's just going to come up in a nice smooth ramp. In this case, it's current limited to about 12 amps, so it levels off. Some vehicles, it just goes up and comes down like a triangle. If I saw it shoot up early and then go over, that indicates problem with the windings inside the coil, high resistance. So you'd be able to see the condition of that coil just by looking at the picture. And then you can stack them together and see the coil and the current and the voltage. And then we have compression. So a couple different ways to test compression. Relative compression's pretty helpful because I don't have to disassemble the engine to figure out where the problem may lie. This we can just do by cranking over the vehicle, making sure it's in fuel cut, and then using a low amp probe in order to check the current flowing through the starter based on each cylinder. right? Because a higher current draw means higher compression, lower current draw is going to be less compression in that cylinder. Here's an example we did on a Jeep where you see there's cylinder 1 there, and there's cylinder 1 there. 165432 is the firing order on this. So 165432, and you see every odd number cylinder has low compression on it. So why is that? And then we have high compression on the others. There's a low pressure pulse and low vacuum pulse, so it's not pulling in the vacuum. In this case, this vehicle had a clogged cap, so it wasn't able to release the pressure in the cylinder as quickly. Somebody made a really good analogy in a comment I saw on the last time I did this. Think about it like a clogged drain, right? So I got a clogged up drain. The water's not going to drain as fast. It'll still drain maybe, but it's not going to drain as fast as a nice clear drain. So if I have a clogged cat, same idea. The air can't get out, or the exhaust can't get out as fast. So I want to evacuate the cylinder, so I can't pull in as much fresh air. So I'm going to have lower compression. So relative compression is going to tell us roughly where it is, or at least I can tell what cylinder it is. In that case, it was stuck to one bank. That's a pretty telltale sign that you got to look at exhaust on that side. Running compression can tell us a lot as well. So if we take a look at this signal here, this is off of the, this is using a 500 PSI pressure transducer and the pressure adapter with a Zeus Plus. And we can see here is the compression event. So pressure is rising in the cylinder. There we get to top dead center. Once the ignition event is usually a little bit before top dead center. We'll see that in a minute. Once it does that and the ignition occurs, it will then come back down. It'll drive that cylinder down. So my pressure gets lower and lower. Eventually should go in vacuum. And then it's going to come back up to exhaust. I can actually see the 3 pressure pulses from the other cylinder in there on the exhaust side of things. And then the intake valves will open somewhere around here. And then I will see my fresh air come in along with the fuel. I'll probably have a little bit of turbulence in there. And then it starts back over again with another compression stroke. So we do not want to see this go up over 0. If it does, because it's if the exhaust valves are open, it should be open to atmosphere, right? So I shouldn't see anything over atmospheric pressure coming out. So this is kind of how the pressure transducer works relative to ambient air pressure. So 14.7, if you're at sea level, it's roughly 14.7 psi. It'll call that 0. And then our reference is off of that. So if I see anything going over 0 in the exhaust side of things, suspect a clogged cap. Here's a good example of one that had like no compression at all on one of the cylinders. I don't know what the cause was, mechanical of some sort, I think, but it had no compression whatsoever. Everything's below 0. It barely made a pressure pulse over 0. This is on a bad cylinder, and then a companion cylinder to it. That's a known good on the companion cylinder there. So we can definitely see the difference between that one, where it's not building out that pressure pulse at all, versus this one where it is building a nice, good compression pulse, vacuum comes down, exhaust, intake, and so on and so forth. So that was a good example on the same vehicle. And then here's that Jeep I was talking about before, exhaust stroke pressure above 0 psi, and it was steadily rising. And then it wasn't able to pull really good vacuum, didn't have really good vacuum pockets on that cylinder, so that was indicating that clogged cat wasn't able to get that exhaust out of there fast enough to make room for more air. And then I just wanted to try on my own car, put it all together. Let's put our air, fuel, ignition, compression all together on one screen. So here's my compression. Here's my current ramp for my ignition coil. So the ignition event happened about here. Probably should have brought it up, but that's okay. It happened, like over there. Then the combustion occurs. I get a vacuum pocket. There's my exhaust, 1, 2, 3 other cylinders. Then the fuel injector, of course, sprays slightly before the intake valves open, so it sprays over here. Then the intake valve opens, and you can see that I have some turbulence in there, and there's a little crossover in there. And then when it pulls back down, and then my compression event starts again. So you can see everything going on inside that cylinder without having to take anything apart. Just take a spark plug out, put a compression gauge adapter in there, put the pressure transducer in there, and you can see the pressure going through the cylinder. Pretty helpful. Those are my slides. Let's go live. See what we can see on the tool. So I have 4 different vehicles to show you, and a lot of this stuff's going to be on the, well, actually, no, I couldn't say a lot of it. So it's like half and half. Half scanner, half scope. First one's going to be a Ford Escape. And we got some scanner stuff that is unique to Ford. And many Fords have this information in there. So if I go under engine and I go to functional tests and I go to special functions, there's a couple in here. So relative compression test by itself, this is a scanner function. So it identifies the compression problem by comparing the average cranking RPM of each cylinder to the mean RPM of all cylinders. Maximum compression for a cylinder occurs when the crank position sensor signal from the previous cylinder is low. Cylinder less compression will cause the crank position sensor to accelerate more than the other cylinders. So basically it's taking cam and crank relationship versus the mean RPM and telling you which one is weaker. This test is designed to detect only one weak cylinder in the engine. So if you have multiples, it might not work as good. I don't know how far it's going to let me go, but it's going to say apply the parking brake, put it in park or neutral, fully depress the accelerator pedal, the wide open throttle, and hold down the brake pedal. So we're just going to mash both pedals to the floor. For vehicles with a manual transmission, please hold down the clutch and brake while cranking. Ensure ignition is switched on and engine is not running. And then it's going to go, once I meet all these conditions, but none of them are met, once it meets those conditions, it'll crank the engine over, and then it'll tell you percentage-wise who is lower. So it has to meet those conditions, though. Since I can't, because I'm not hooked up to a car, it will not proceed. Relative injector flow test, that's going to be similar. It's going to pulse the injectors. It's going to check for leaks, gross leaks. Follow recommended powertrain control emissions diagnosis workshop manual fuel system pressure release procedures prior to service. On some vehicles, application prompts will be given to cycle the ignition on and off in order to properly prepare the vehicle for the test. You're going to go through, it's going to cycle the ignition, and in this case, it's not going to let me go any further. So I'm going to reload the vehicle. But then it would pulse the injectors there and check for leaks, bleed down on the system. Also under special functions, there is a power balance test. So this is on most Fords at this point. Test in park or neutral. Excessive RPM or rapid RPM changes may cause data loss. Make sure the parking brake is engaged and the wheels are chucked. So it's going to collect data, and it gives us a graphical representation of how those cylinders are adding or subtracting to the overall power of the engine. Now, more than likely, you're not going to see high. More than likely, you're going to see low. Whichever one's misfiring is going to be negatively contributing. So you should see it down there. It also gives you a little history, which is nice. I can also turn the injectors on and off and see if it changes anything. So if I'm looking good here, fairly straight across, and then I disable injector 1 and it does this, then I know the problem is not my injector. More than likely not my injector anyways. Stranger things have happened, but if I turn off the injector and it runs like garbage with that one cylinder out, then the injector was doing its job before. However, if I disable the injector and it runs the same, then maybe that's my problem is the injector. It gives us a place to look. So it's a combo of 2 tests from the Ford factory tool. There's also a misfire monitor and neutral profile correction. Anytime you do anything with a PCM, internal engine repairs, crank sensor, or trigger replacement, you have to do this test as well. So that helps reset the misfire monitor. And then also in here, we have the guided component tests. We go into engine, things like cam and crank, kind of, sort of, are going to help us with that. Ignition tests, I can go in there and do primary, secondary tests on the ignition system. Fuel system tests, check the injector, check the fuel pump, fuel pressure tests. And this one also, variable valve timing, possibly, oxygen sensors, possibly. Fuel systems, probably pretty common. Signature tests. All right, it's going to give you the connector view. It's going to tell you what wire does what. And then if we come down here, it's going to show us what it should be. If I go over to the ignition, it's going to go to ignition and do a secondary test. The coil current RFI test, RFI high output test, and a secondary ignition test. which is going to give us a pattern here. It's going to look kind of like that using the coil and plug adapter. So a lot of different tests I can do there. Next one is BMW. So that has a couple functional tests you may need in that case as well. 2018 3 Series. Functional test, special functions. Whoops, not battery replacement. Yeah, get out of here. All right, hit the wrong button. Exit. Let's see. Injector coding. If you're replacing an injector, you might have to do that. Timing chain test. That's pretty handy. So if you think your timing chain is stretched, that might cause a misfire. You can go in there, and then it'll check to make sure that the Vano solenoids are not the problem. Engine must be heated to a temperature greater than 60 degrees, which it's not going to let me do. But it'll go in and tell you whether or not your timing chain is stretched. Valvetronic, a couple different things for that. Adaptations, you might have to reset some adaptations with that as well. Also in here, under data, you're going to see cylinder status data, which is going to give us misfire data there. So misfire counters, rough running values, things of that nature. So that's in there. And then also in here, we'll have got a component tests. And this one, as many BMWs do, we actually have a built-in relative compression test that you do with the, you can either do it with a low amp probe or you can do it with secondary probe. So in this case, you're just using the test leads that came with the tool, clamp it onto the battery, and then due to the way they set up the test, it's going to give you a cranking pattern on there and see. So that's pretty helpful. So that's on many BMWs. I think they've started adding it to other manufacturers as well, but definitely on BMWs. VVT, fuel system, ignition. So lots of different subjects or suspects there. Then we have this Jeep Renegade. So CDJR can be a little unique at times too. So we're going to load through here. They have a couple unique places where they hide things, put it that way. Got to go through the gateway. We go into engine, and under system tests, we have a which cylinder is misfiring. So you might not think to look there for a misfire test, but it is under system tests. And then it'll give you the misfire counters. Now I know this is a 4-cylinder. Since I'm in demo mode, it's going to give me all 8 cylinders no matter what. But it's going to give you your misfire counters in there. So that is fairly unique. And then in data, cylinder imbalance detection monitor as well, which should give us a couple things like that. Fuel controls may be helpful. And then kind of component tests. I'm going to see the usual suspects in engine. So fuel system, you're going to have your injector, fuel pump relay, ignition coil. All right, do a current ramp test, for example. Just going to show you how to do that. And then lastly, we have the Santa Fe. And the Hyundai has a unique test in there as well. And it's not in engine, but there is some engine stuff that we can look at. System tests, you may have to do reset adaptives at some point after you're done. Functional tests, maybe you need to cycle the fuel pump relay. Individual injector to disable and enable. Same with coils, enable and disable coils. Variable intake solenoid, perhaps. Some of those things may cause misfires. But unique to Hyundai and Kia at this time is there is a cam crank relationship test in here. So people always ask, hey, who has a known good cam crank relationship test? This one's actually preset for you. So crank and cam sensor signals, black to known good ground. And look at the relationship between the two channels and see how they match. So that is a lovely thing. All right. So that is misfires. How to test misfires in various ways. Because we need to have the 4 main ingredients, and if one of them is out of whack, then that will give us problems down the road. All right, let's talk about next week. So next week, we are continuing our OEM-specific ADAS training and going on with Tesla. And Tesla has some unique things in there, Notably, one of them is this camera, which they share across many of the models. It is a 3-lensed camera, so no problem. We'll go through that just as we've gone through many other manufacturers with that. Same time and same place, every Tuesday, 6 and 9 Eastern. If you want to join on Zoom, go to snapon.com/OT. Otherwise, the 9 p.m., 6 p.m. class goes live to our Facebook page, YouTube page, youtube.com/snapon diagnostics. If you scan that QR code, it'll bring you over there and subscribe you automatically. If you're watching the video on YouTube, please make sure you like and subscribe. And the 9 p.m. Eastern class goes live to our Facebook page. It's Snap-on Diagnostics product and training. If you want to see any of the other topics in this series, we're up to 126 episodes so far, anywhere from intro to ADOS through EVAP system diagnosis and everything in between. They're all free. They're roughly half hour, 40 minutes, depending on how much material there is there. So definitely worth your time if you want to learn up on some other stuff. Also, do we have your email address? If we don't have your email address, you may be missing out on some important diagnostics-related content like tech focus articles, short track plugs, quick tips, new product releases, etc. Did you know we've released 2 new products this year? And we've released 2 new software releases this year. And I've had 20-something new classes come out this year. So they will tell you what the schedule is for my classes as well. Here's an example on a tech focus article on diagnosing a timing chain. So lots of good information there. And once again, it's all free. You scan that QR code, it'll bring you to a page where you can fill out your information and start receiving this valuable information. With that, let's get to questions. If you do have a question on Zoom and you joined a little late, just feel free to use the Q&A button. Looks like I do have a question there. If you are on YouTube, feel free to use the live chat. Let's see what we got for a question. Jay McCall, thanks for the class. You're very welcome, Jay. As always, thanks for attending. Do appreciate the regulars and appreciate the newbies too, but the regulars really take a lot of time out of their day to continue learning, and I appreciate it. And hopefully if you are new and you liked it, then you'll become a regular. And then we go over to YouTube, and we have a couple regulars over there too. So the Winton is checking in saying hello, and Nick is saying hello from the UK. It is laid out over in the UK. Time for bed, Nick. Glad we can provide this free training for you. And I know you appreciate and enjoy it. So thank you very much for that. That clears out the questions. So with that, thank you very much for taking a little bit of time out of your day to spend a little bit of time with me. Hopefully you learned a few tips and tricks on diagnosing misfires. Hopefully I'll see you next week for OEM ADOS on Tesla. With that, enjoy the rest of your week. Enjoy your weekend. Have a nice night and take care.